for joining us for today's webinar entitled COVID-19 Mitigating Airborne Transmission with Effective Ventilation Strategies. My name is Rob Fernandez, and I will be the moderator for today's webinar. I am the manager of IAQ, indoor air quality, mold, and microbial contamination at the company. And along with my colleagues at ECHO, we have been involved in evaluating pandemic readiness of various organizations and recommending mitigation measures, and also being involved in disinfection projects as well, where there have been positive cases. ECHO also continues to provide our full consulting service during these challenging times, including hazardous material consulting, occupational health, and environmental consulting services. As we've seen in the media recently, several agencies, including the CDC in the US and the Public Health Agency of Canada, have begun acknowledging the potential for aerosol transmission of SARS-CoV-2. Potential for aerosol transmission has subsequently drawn further attention on the need for good ventilation and the role that HVAC systems can play in mitigating against the spread of COVID-19. I'll briefly now introduce you to our presenters today. However, in the interest of saving some time, do please look at their profiles. If you click on their photos in the invitation for the webinar, you will be linked to their LinkedIn accounts and be able to see their background and experience. Our first presenter will be Marianne Levitsky. Marianne has been at the forefront of keeping on top of this latest research and developments during this pandemic, and has presented or been involved with numerous webinars to date, both with ECHO as well as WHWB, Workplace Health Without Borders, an international nonprofit that provides occupational health consulting in developing countries. Although ECHO has presented ventilation information in the past webinars, as we've been an advocate of ventilation as an important aspect of the pandemic since the beginning, we are fortunate today to have Matt Forsyth, an experienced building services engineering firm, join us today to lend their expertise to the discussion. From Matt Forsyth, we have Raphael Very, President and CEO, joining us. Raphael is a mechanical engineer with over 20 years of experience. We also have Dr. Malik joining us as well as one of our panelists. He is the CEO of the company, has been very much involved in all the pandemic consulting that we provided to date, and presented in various webinars, which you may have seen in the past. Before we get started, I do have a few housekeeping items. First, we do kindly ask you that you leave your questions until the end. We will be muting everyone, and you will not be able to unmute yourself. However, if you do have questions during the presentation, please enter them in the Q&A box at the bottom of the screen, and we will take them up at the end of the webinar. You can also, if you want to ask your questions in person, you can raise your hand at the end of the presentation, and we can also go through the questions as they come up. We also please ask you to fill out the survey at the end of the webinar that was attached to the invitation. We appreciate any feedback you can provide, and it does help us kind of figure out what topics we should be covering in the future that may be of interest to our attendees. And with that, I will pass the webinar over to Marianne.
Thank you so much, Rob. And I'm going to talk to you a little bit about what we're calling new thinking about aerosols and COVID-19 as an introduction to Raphael, who will talk about ventilation. Clearly, there's a link between aerosols and ventilation, and we will tell you about it. You may be wondering why I have the word new in parentheses, in quotation marks, which I'll explain. I think the thinking is not really new. What is new is that aerosol scientists and infectious disease specialists are talking to each other. And this was exemplified by Dr. Anthony Fauci in the US when he presented to Harvard Medical Rounds on September 10th of this year. And he said in the past there was some misunderstanding about respiratory droplets and so-called aerosolized particles. And he said that they're now talking to aerosol and particle physicists. I'll let you read the rest of the quotation another time, but he says the bottom line is there's much more aerosol than we thought. Now, just in case you think this is new, here is a quote from a review of a book published in 1955 called Airborne Contagion and Air Hygiene by William Wells, who was a seminal thinker in this area. And he spoke about the importance of small particles, what we now call aerosols, and their importance in infectious disease. And he said at that time, he didn't think that the respiratory droplets were that important. This discussion continues today. So we have seen some recent changes from public agencies. For example, the US Centers for Disease Control recently changed their website, and they now say that infections with respiratory virus are principally transmitted through 3 modes: contact, droplet, and airborne. And I do want to caution that the word airborne has kind of different meanings in the infectious disease world. So I would direct you to the CDC site to learn more about that. So the CDC goes on to say, there are several well-documented examples in which SARS-CoV-2, which is the virus that causes COVID-19, appears to have been transmitted over long distances or times. And especially when an infected person was present for up to 30 minutes or longer in an enclosed space. And in such a case, the virus caused infections in people who were more than 6 feet away. So while CDC says those occurrences are uncommon, they have in fact been responsible for a large number of infections, because when they happen, many people get infected and then those people go on to infect others. So the most famous of these perhaps was the Biogen conference that occurred in Boston in the early days of the pandemic, which was now thought to have been responsible for infecting 20,000 people. In Ontario, we're familiar with a very recent outbreak at SpinCo in Hamilton, where many people were infected and many secondary infections occurred in a spin class where it's very likely that it may have been because of a buildup of virus under poorly ventilated conditions when people were exercising and therefore breathing fairly heavily. We also know there are many cases in which a choir practice infected a large number of people. So while this may or may not be uncommon, we know it can be responsible for very many infections. In Canada, while the Public Health Agency has not changed the advice on its site, Theresa Tam, the head of Public Health Canada, did say in a briefing on October 13th that outbreaks do occur in enclosed, poorly ventilated places, and that points to aerosols. She said, as a result, we should learn to avoid the 3 C's and make sure the ventilation system is serviced. So she is acknowledging the importance of ventilation. And what does she mean by the 3 C's? Well, this is a concept that was publicized in Japan and has been adopted by the World Health Organization and others, and WHO has put out the poster that you see here, telling you to avoid crowded places, close contact settings, and confined and enclosed spaces with poor ventilation. So clearly there is a concern growing among many people that ventilation is important. So I apologize, I'm having some trouble changing the slide. So Chanel, if you can step in and change the slide. Thank you. So what is this whole discussion about? It tends to be largely about droplets versus aerosols, which is largely a matter of size. And this is where we do have some disagreements between infectious disease specialists and aerosol scientists. So what do they agree on? Well, they do agree that droplets settle rapidly. They act like ballistic projectiles, that is, they spray onto the face of another person. And that is an important route of transmission. Aerosols are smaller than that and can remain suspended in air for up to hours. The infectious disease specialists have been calling droplets those particles that are larger than 5 microns, that is 5 micrometers, and they believe that droplets are the main route of transmission of SARS-CoV-2. The aerosol scientists, on the other hand, say droplets are greater than 50 microns because they say if it's as small as 5 microns, it's not going to fall so quickly. And what's more, the larger droplets rapidly evaporate and become smaller aerosols. So they say the aerosols, that is the smaller particles, are the main route of transmission. So nobody's denying transmission can occur through droplets, it can occur through aerosols. It's kind of really an issue of which is most important. Again, next slide, please. So here's a little diagram that explains it depicts the difference in sizes between 50 microns and 5 microns, and that little dot inside the 5 micron droplet is the actual virus. And just click on this again, I have a, please. Dr. Jose Luis Jimenez of University of Colorado, who is the aerosol scientist that I would encourage you to read, pointed out that for aerosols of 5 micrometers to fall to the ground quickly, the gravity on Earth would have to be 100 times larger than it is. This can happen on some stars, but on Earth, he says, a 5 micrometer aerosol can actually stay suspended in the air for 30 minutes indoors. Next slide, please. So one thing the aerosol scientists, infectious disease folks do agree on is that risks are higher in close contact. So they also agree that a range of particle sizes are emitted during different kinds of activities, including just breathing, speaking, singing, coughing, or sneezing. And because of asymptomatic transmission, we know that many people transmit COVID-19 when we don't know or they don't know they're infected. And because they're there for coughing or sneezing, we're mostly concerned with them doing things like breathing, speaking, maybe singing, maybe shouting. But all do agree that whatever they're doing, close contact to other people results in higher risk. The infection control people say because that happens because the droplets spray onto the face of the other person. And the aerosol scientists say it's because the concentration of aerosols is higher in close proximity. So either way, you shouldn't get close. That's the bottom line. Okay, so what does this mean? Again, next slide, please. Now, another concept we have to think about in this regard is the idea of infectious dose. And that's simply the amount of virus needed to establish an infection. So we know that airborne transmission occurs when particles are inhaled at greater numbers than the infectious dose. There are estimates of infectious dose for SARS-CoV-2, but we don't really know for sure. They're really estimates. But we do know that the type of activity is important and that more virus is emitted when people are exercising, think of the SPINCO situation, when they're speaking loudly, when they're singing, think of the choir situations, when they're shouting, and of course, when they're coughing and sneezing. And the other side of the coin is if people breathe more rapidly and more deeply, they're going to inhale more of the virus. So this is important. Activity is important both for the amount emitted and the amount inhaled. The other thing to remember is that masks can reduce but not eliminate the amount of virus that is emitted and inhaled. So when we think about ventilation, it's really important to think about, are we going to keep exposure down below the infectious dose? Next slide, please. And this is a diagram from a blog post by another professor named Richard Corsi, and I would encourage you to read this. And he explains this through this diagram. So what he says, just as I showed in the previous one, here's some stick figures. I think you can see my cursor. And here's the person emitting infectious aerosols, particles, droplets. And here's somebody standing very close. So they're in the plume of this person emitting. So the green dots are the droplets. They're falling to the ground, but they're also hitting that person a little bit. This is what we call near field exposure. Ventilation is not going to help you very much in this case. This person is not, unless you had a local exhaust ventilation and put this person in a hood, which might happen if you were in a hospital, but in a regular social situation, you would not find that that ventilation would help very much in near field exposure. But what we have here is if those aerosols then disperse throughout the room, in the absence of good ventilation, they could build up to a critical concentration that may equal the infectious dose for people in other parts of the room. And here, this stick figure over here is representing someone who is in the far field exposure. And that's where ventilation becomes important. So this other diagram, Raphael will tell you a lot more about the ventilation, but kind of depicts some of the considerations that you might have in providing sufficient ventilation to make sure that far field exposure is not going to exceed the critical dose. Next slide, please. So what does this mean in terms of ventilation? Well, ECHO has researched this a lot to try to provide some guidance and guidelines for ventilation. So we started looking at ASHRAE. ASHRAE is the American Society of Heating, Refrigeration and Air Conditioning Engineers, which is kind of the premier body for ventilation recommendations. So they have two types of recommendations. One is their standard 62.1. This is actually a fixed standard. It's often incorporated into building codes, and it was pre-COVID. It is not to protect against COVID, but it still is important. And what it says was that it has a range of different kind of ventilation rates for different situations. For offices and most public assembly places, they say you have to have 5 cubic feet per minute of outdoor air per person, plus 0.06 CFM outdoor air per square foot of occupiable area. So that's kind of a bottom line, not really related to COVID. But in addition, ASHRAE has recently produced some guidance specifically for COVID, which you could not call a standard, but is just a guideline. And they, so that they do recommend as much outdoor air as the HVAC system can handle. And they also recommend MERV 13 or better filters, and Raphael will talk more about what MERV 13 means, if the air is recirculated. And they also recommend a relative humidity of 40 to 60%. Now, ECHO has researched more on this because ASHRAE's guidance does not really talk about how much ventilation is needed to protect against COVID. And of course, this is very new territory, and there aren't really very absolute guidelines for this. But we have looked into the best available advice, and this is some of what we've come up with. So some of the experts are recommending 20 cubic feet per minute per person. And then in larger rooms with multiple people, such as classrooms, this recommendation is from Harvard, 5 air changes per hour. And that is not necessarily all outdoor air. ASHRAE did say if your part of this is made up from recirculated air, you need MERV 13 filters or better. In addition, to make sure that we're having enough outdoor air, ECHO is recommending a maximum carbon dioxide target of 800 parts per million. So with that, I'm going to turn it over to Raphael, who will tell you a lot more about ventilation. Thanks very much.
Thank you, Marianne, for that wonderful segue. And thank you, Rob, for that previous introduction. So today, we're going to talk about ventilation. I'm from Mat Foresight Engineers. We're a building services engineering firm. And as Rob mentioned, my background is 20 plus years. I don't even want to say exactly how many years anymore as a mechanical engineer, with a lot of emphasis in the HVAC space. And we've had the opportunity to do this for a wide variety of client sectors, a lot of different building types. And, we've been doing this at all stages, whether it's new construction, renovation, capital improvements, commissioning. So we understand that full life cycle and some of the headaches that building owners go through. And our mission is to help you create your best building. And today we're going to be talking about helping you create a safe building. And the 3 areas we're going to focus on is ventilation, filtration, and control. So let's keep in mind 3 specific concepts. Dilution. Dilution is going to be analogous to ventilation. Removal will be our filtration component. We want to try and remove things from the space. And then for this discussion, controls will be the most analogous thing to containment. So Marianne provided some really good examples of some previous case studies where the virus has spread. Here's a couple more, just to show you some graphic representation of that. This was an 11th floor area in Seoul, Korea, multi-story building, 216 employees. It started with 1 infected person. It didn't take very long to have 94 out of 216 people infected. And you can see they're all primarily concentrated in one area with a very small exception in another area. That really speaks to how this thing can move when it's aerosolized and it's in the air. Here's another example, a wonderful CFD put together by others. And, again, you have 3 tables side by side by side, 1 infected person. They all went for a nice dinner. An hour and a half later, not only were they full of food, but they were full of a virus. All 3 tables were infected with that virus by the time they left, all starting with one infected person. So this thing does get into the air, and it does move around, and your air patterns in your space are very important in how those things move around as well. So Marianne did a great job kind of explaining ASHRAE 62.1. We actually used the 2010 edition in our Ontario building code. I've provided a very small snapshot of the table on the right. And you know, that calculation is broken down into an area component, a people component, and then we also have to understand the effectiveness of the zone or the efficiency of the system that's delivering that air. So, you know, if you're a building owner or operating a facility, you know, you really want to ask the question, are you providing this air right now? That's really what you want to know. And also, as Marianne had mentioned, for COVID, ASHRAE is recommending, you know, they want us to be safe. They're saying provide as much outdoor air as possible. That's kind of the guidance. And as much as allowable by the equipment. So we'll get into that in the next few slides and talk about what that looks like and some of the impacts and some of the things we can do to mitigate those impacts. And one thing I would like to point out, you know, it is the minimum ventilation requirement. A lot of times those minimums end up becoming our maximums when we consider peak design days. So if we look at, you know, the coldest day in the winter, the hottest day in the summer, you're going to be hard pressed to find systems that provide more than that minimum amount of fresh air on those days. So let's talk a little bit more about this. So the impacts of outdoor air, of increasing outdoor air. We know first and foremost, the whole point is to keep us safe. It's going to create a safer environment, period. You're going to be able to replace that dirty air with cleaner, fresh air. And there's things we need to do to accommodate that. And we know that it's going to increase demand on our equipment as we do that. The table on the right kind of demonstrates a typical coil, same outdoor air conditions, and what that loading means when we increase the percentage of fresh air across a coil, which ultimately impacts our systems. So if we go from 20% to 90% fresh air on that coil, you'll see that the load on the coil doubles. The chilled water flow doubles, and the pressure drop, the water pressure drop across that coil goes up by almost 2.5 times. So there are significant impacts to your system. It is going to, you know, rob your sensible cooling capacity for the rest of your equipment, what's available to them anyway. So you really have to understand what you can do with your building before you choose to just bring in a lot more fresh air. So let's talk about some strategies on what we can do with that. So one of the things that we can definitely do, and it's not dependent on your peak loads, is maximizing the use of your airside economizer, you know, your free cooling modes. You know, whether or not you're doing dry bulb control, enthalpy control, combination of the two, really looking at what that system, how it currently operates. Is there a way you could stretch that for longer? That would definitely help. And again, those are traditionally done in periods where you don't have extreme temperatures. So that can really help you and your building occupants. We also want to look at potentially some control strategies where we reset the outdoor air damper positions depending on what your indoor space is doing. So you might start by trying to increase that outdoor air, monitor the inside, and see if, you know, are you getting temperature and humidity where you want it in that space? And if not, if you can't control it, you know, start dialing back the outdoor air. There's some specific sequences you can write into your building automation system to allow that to occur. We would also recommend, you know, a bit of a trade-off here. If you're increasing the amount of outdoor air, again, you're increasing that load, you're increasing demand. Potentially changing the set points in your space might also be helpful. You know, in the winter, you know, drop that temperature sensor setting by a couple of degrees, maybe increasing that in the summer by a couple of degrees. Again, it's going to help offset that energy penalty. And, you know, you should have that conversation with your tenants and occupants and say, look, it's going to be a little less comfortable, but still reasonably comfortable in your space. We're doing this so that our system can bring you more fresh air and keep you safe. I think most people will be willing to accept that trade-off. We're also going to talk about demand control ventilation. We'll get into detail on the next slide. And I just want to point out that whenever we're making these changes on the outdoor air side, making sure that we're doing the same on the exhaust side. You can't bring air into a building without getting it out. So, you know, a lot of buildings with really good, robust dynamic systems, dynamic control systems, they should be able to accommodate that kind of automatically. But some systems are a little more archaic. Maybe this has to be done manually. It really needs to be looked at closely, because you don't want to change those really important pressure relationships that you have in your building, which are really designed to keep you safe. So we certainly recommend, you know, part of this entire process, you want to measure, confirm, and adjust the airflows in your space to make sure that you're meeting the requirements that you need to make. Hire a qualified TAB company, get some additional support, making sure that all that's getting done the way it's supposed to get done. So I want to touch on demand control ventilation. So generally how this works is it's going to monitor the CO2, so carbon dioxide buildup in your space. And there are a variety of ways how this is monitored. And if we look at what has the best control versus what has the least amount of control, the space sensor has the greatest control, then zone, then the general, which ends up, you know, somewhere in a return or exhaust duct, depending on your system. When you have those types of systems, the CO2 really gets diluted and you don't really get good information as to what's happening in a specific area. So whenever you can, you'd want these in your space. You know, when we talk about how to properly set these up, and this really goes for all VAV systems, anything that's got modulating outdoor air control, never have a 0% VAV setting when it's an occupied space. You can't do that. So when we talk about the outdoor air calculation, remember there's two components. There's area and there's people. So your minimum position when a space is occupied always has to cover off that area air that you need. And the only thing that modulates is going to be the demand of the people. That's kind of what that graph on the right side of your screen shows. So when we talk about what we do with this, because there has been some back and forth in, you know, the ASHRAE community and even REVA, and you know, initial indications were not to, you know, disable DCV, but now, you know, with some more science and some more background, the idea here is dropping your set point. So, you know, a typical office setting would be something on the order of 1,000 ppm of CO2 as your set point to allow the demand control to start kicking in. The indication here is if you drop that by 800 to 800 parts per million, not by, sorry, so dropping it by about 20%, it's going to improve your response time. It's going to allow the fresh air that you need to get into your space much quicker. So that's going to help with diluting the space with outdoor air. I also just want to briefly touch on occupied standby modes. These are quite popular. Essentially, you have a floor which is scheduled to be occupied, and in all these individual rooms, you might have sensors, and these sensors are occupancy sensors. And typically, even though the floor is supposed to be occupied, the sensor itself will tell you the room isn't occupied right now, set my VAV to 0, because basically it's saying it's unoccupied, there's no one there. That's great under normal conditions. Under these pandemic conditions, the guidance is not to use those, it's to disable those. So, because you might get people that go into that space, then that system has to recognize the people walking in and ramp up. And that ramp up time just isn't fast enough, even if you change this setting here from 1,000 to 800 ppm. So the guidance there is to disable the occupied standby modes on the HVAC system. It's got nothing to do with the lights. They should run independently. Now for constant volume systems, you know, large single zone demand control ventilation systems with serving multiple rooms are a lot trickier to control. So the guidance around that right now is essentially to disable that. The easiest way to do that is just make your setting 400 ppm. That's very clean outdoor air, probably cleaner than you're actually going to get downtown. And the reason behind that is because you don't have that dynamic control downstream from your air handler, you won't be able to monitor and regulate how much fresh air you get into each of the individual rooms. So again, the guidance for single zone constant air volume systems basically disable your DCV. That doesn't mean don't put fresh air in there. You definitely have to do that. And we want to make sure that we're calibrating existing sensors, replacing old sensors. You know, there is a maintenance aspect to CO2 sensors, so making sure that those are working is very important. So I just want to draw attention here to this slide. You know, Marianne had mentioned, you know, air change rates and how important they are. So what we have here, the graph on the left kind of demonstrates different quanta levels. What quanta is, it's the viral load that gets expelled in an hour. And, you know, we don't quite know yet how COVID lies when people are, you know, in different situations, how really infectious it is. But we have, you know, some idea that it might be similar to influenza. Anyhow, so what this shows here is different rates of quanta, and you can see how the air change rate impacts the percentage of infected people. And as we start to get, you know, from 6 air changes and beyond, there's a rate of diminishing return there. So that's where some of that science comes in that Marianne was alluding to before. Table on the right demonstrates the different variations in quanta based on the activity. So, you know, here right now, you might say I'm loudly speaking. I'm expelling, you know, 61 quanta per hour. If I was, you know, doing heavy exercise, I might be up at 408. I mean, that's why you see, you know, that spin class, why that was shut down, right? That's a huge increase in quanta. You know, hard to deal with that with respect to ventilation and almost anything. So the activity definitely impacts the space and the people. So I wanted to talk about, you know, a typical, you know, commercial office environment. There's a lot of analogies here to different spaces as well, or they're analogous to other spaces, I should say. So if we look at, you know, a traditional 1 CFM per square foot type system, if you're in a 10-foot office ceiling, you're talking about 6 air changes an hour. And you can see that it's over on the graph on the left. It's categorized under lab because it's actually sort of a medium density, medium loaded office. This graph was done by a firm out in California, and they have much stricter requirements to use a little bit less air. So we're closer to lab setting in their eyes than anything else. And when you look at that, you know, and if you look at the typical 62.1 ventilation rates, those just the outdoor air ventilation rates, you know, we're hitting about 3/4 of an air change an hour under this scenario. So, you know, we're close to that 1 air change an hour on outdoor air in this setting. And I just want to show that on that graph, you can see how the CFM really impacts the probability of infection, right? So if we're at that 6 air changes an hour, you get down to about 1.25%. And that's, again, assuming, you know, MERV 13 filters, having a quanta rate of about 10, which is kind of on the low end for influenza. And you can also see that masking up, which is the red, you know, drops that by more than half. So, you know, masking up, good ventilation rates, you know, can't say enough about that. That's definitely a must. Filtration is definitely the next big topic here. So MERV stands for the minimum efficiency reporting value. That's all that is. So the table here on the right, that's a table from ASHRAE, and it kind of sets out minimum efficiency requirements. These are kind of the standard ranges. And there's a lot of specific testing that goes into ASHRAE so you can qualify for these MERV ratings. Now, you'll note that, you know, on this table, anything that has a MERV rating under 11 can't even deal with a particle range that's between 0.3 and 1 micron. It's not even applicable, right? So we're starting to build the case here for having better filtration, because as you saw in Marianne's slide, these particles are small. Yes, some of them are contained in larger droplet nuclei, but the particles we're dealing with can be quite small, and we want good filters to make sure this all works. So this slide here, graph on the right, is measured performance data on commercially available filters. So this is, the previous slide is sort of the EPA ratings on your vehicle for fuel efficiency. This is analogous to real world performance. So you could see that some of the, I'll say lesser filters do have some capability in the smaller particle ranges. But when we compare the performance, there really isn't much of a comparison here at all. I mean, if we look at, MERV 14 is 2 times more effective than a MERV 8 when we're dealing with 1 micron. It's 3 times more effective than MERV 8 when we're dealing with 0.3 microns. So, there's definitely value in moving towards better filtration. And to further reinforce that point, Wells Riley did a great study on this. They did 9 different case studies, 9 different environments, and they looked at office buildings, schools, hospital waiting rooms, and they looked at 3 different viruses: rhinovirus, tuberculosis, and influenza. So there's that varying quanta rate, just to kind of capture, the fact that we don't really know what's happening with COVID, but it's probably somewhere in this range. And you can see that you look at that red line, that's the average of all of them. And you can see that once we get beyond, once we get greater filtration than MERV 13, there's again that sort of rate of diminishing return there, where we can really reduce the risk of infection. And you can see there is quite a significant drop from a MERV 7 down to a MERV 13, and MERV 8 would be very close to a MERV 7. And when we compare these percentages, using a MERV 7 compared to a MERV 13 filter poses a 47% greater risk to the occupants in that space. Compared that to MERV 14, that's a 51% difference. So they are definitely significant differences here in the filters. So the obvious cost here will be, obvious question will be, what's the cost? So what we have here, again, same study, is the relative cost of filtration. Broken down into 3 elements: your relative labor costs, filter costs, and fan energy costs. And I'd like to draw your attention to, MERV 13 and MERV 14, they're very similar outcomes. They get there a little bit differently. One has a higher labor rate, one's got more of a fan energy cost associated with it. But there isn't a significant premium over a MERV 7 when you look at that total life cycle cost. And that's because, MERV 7, you're replacing them more frequently than you are with a MERV 13 or a MERV 14. And, when we talk about HEPA, because that's a question that always comes up, you can see that, it's very, very expensive to run a HEPA system. So this, again, the same study, this graph is amazing. And what this is, so you have your mean relative risk of infection on the left side of the graph, and across the bottom, you've got an annual cost. And the cost is $1 per hour of infectious droplet nuclei. That's too much to remember. Let's just think of it as a cost. It's just a unitary number, right? So, and this was comparing the impacts of filtration and outdoor air to get to the same mean relative risk. So if we look at, MERV 13, it's about, about a 0.5 mean relative risk, and it's at a cost of about $170 an hour. Sorry, $170, but that's our number. Compare that to, we'll talk about Chicago, which is the closest thing we have to Toronto. That's closer to $480. That's a drastic difference. That's a 3 times difference to try and achieve the same level of risk mitigation when you compare filters and outdoor air, right? So that's a big difference. Yeah, so we'll just move on. So there are some considerations for increasing, these are some of the considerations when we talk about MERV ratings. So increased fan power for the same airflow. That's definitely something that you gotta be concerned with, right? However, can your existing equipment handle it? Does your motor have the power that it needs? If it doesn't and you need to replace it, are you having to worry about wiring, circuit breakers, the rest of the infrastructure? And if you can't make any of those changes and you're stuck there and you throw in a different filter, then you're going to reduce your airflow. So there's always going to be this trade-off, and you really got to make sure that you're looking at the specific performance of the individual filter before you put it into your system. And I'm not just talking about grabbing any MERV, anything off the shelf, whether it's a 13 or 14. You got to look specifically at initial performance, final performance. You got to look at the whole spectrum. What types of particles is it good at filtering out? Because again, as you saw, real world performances can vary. So making sure that you pick the right filter to move forward. And when we're looking at DX equipment, refrigerant equipment or gas-fired appliances, if you already have systems that are borderline in terms of their performance, where you see that they typically trip off because of low airflow, if you start to put a higher capacity filter in, you're going to have more issues. You might even run into a situation where if you're running DX and you don't get enough airflow across that coil, you might blow your refrigerant charge, right? So we want to be mindful of that. And then many existing systems can't accommodate that increased airflow. So again, you really have to understand what your existing system is before you start making some of these changes. So we're going to talk about other technology here. So let's talk about UVGI, which essentially uses UVC light spectrum it destroys mold, viruses, bacteria. It's been around for a while, but I think sometimes it's a little misunderstood. So what's important regarding this technology is the effective dosage that you're introducing. And the two primary elements are intensity and duration. So the intensity being how powerful your bulb is, duration being how long whatever it is you're trying to clean is exposed to that light. And in this realm, not all systems are created equal, and they're not always designed to do the same thing. So when you're looking at trying to apply an induct system or in-air handling system where you're just treating the air as opposed to coils, you have to really focus on getting higher intensity because you have very limited space in air handlers, usually only 2 to 3 feet, where you might be able to install something like this. And when you're dealing with that type of space, you're going to have to get close to 10,000 microwatt per centimeter square intensity. Very, very high. Some systems can do it well, other systems can't. Other systems, you'll have to stack that area with so many bulbs that you're really going to impact your airflow. So really understanding how that system works, working closely to make sure that you're getting the right system for what you need is very, very important. And you want to make sure that you're also paying attention to what other materials the UV light might be exposed to, depending on the types of filters, cables, gaskets. There's a wide variety of things you need to consider when you're introducing UV light. But it's definitely been proven to even improve the filtration effectiveness of systems. And I guess two final notes is, whenever you're dealing with UV light in your handler, you have to develop, safe work procedures. You don't want someone walking in there when that system's on. And then there's always the maintenance costs or maintenance time associated with this. Some systems require bulb replacements once a year, some are, maybe twice a year. So really understanding what you're getting before you install it is important. So there are also facilities where, there's just low airflow, low ventilation. You can't really get the air changes that you need. So, what do? There are still some options. Rob presented in his last webinar, you could bring in standalone HEPA filter units that's definitely an option. And he covered that extensively in the last webinar. So in this webinar, I want to talk about upper air UVGI. So this is a system where you're putting in lights at a high level. They recommend a minimum of 7 feet above finished floor. I have someone in my office that would beg to differ because that would probably hit him in the forehead. So, you'd have to really understand your space, but the idea is, a minimum 7 feet, you might have to install a little bit higher than that for it to be installed safely. And what this does is it treats that upper air region in your space. And the reason this is effective is, again, there's that exposure time. It's there, you can shine it for a very, very long time, so you don't have to use a ton of intensity. So, studies have shown that, hitting that space with 91 microwatts per centimeter squared has the same effectiveness as treating that space with 10 air changes. So it really is quite effective. Obviously, there's going to be a cost associated with this. And when you compare this technology with something in the airstream, it is more expensive. We're talking something on the range of 8 to 15 times more expensive to install and 5 to 10 times more expensive to operate. So another system that's a lot of people have been talking about, I know specifically in our GTA region, is bipolar ionization. Studies have shown that it can enhance the collection efficiency of existing filters. It's been shown to inactivate viruses, pathogens, mold, bacteria. There's an element of odor control associated with it. And, depending on the system's cost could be, similar to in-air UVC. There's always the question of ozone generation. Is it or isn't it generating ozone? So the CDC has actually provided a formal response to ASHRAE with respect to bipolar ionization. And essentially, they're not promoting it. They're not pushing back against it. All they're saying is if you're going to use the system, it has to meet UL 2998, which is the environmental claim validation procedure for zero ozone emissions from air cleaners. So their position is if it meets that UL listing, then it's safe to use. Another option is a particle control system. So this is, essentially a really fancy electronic air cleaner. It uses electrostatic field manipulation. Again, and I can assure you it's not the same type of system that you would have in your home. It provides MERV, the equivalent of MERV 15 efficiency. And it has even been shown in some studies to enhance the efficiency of even HEPA filtration. So again, similar in that it inactivates viruses, pathogens, bacteria, and it's good at odor control and removing VOCs and TVOCs. The electrostatic process does not generate ozone. And again, the costs are going to be similar to the other technologies. So I just want to touch on humidification. Honestly, don't let it get too dry. So ASHRAE recommends 40% to 60% RH. There are design guides where they indicate, different building types have, less RH as a minimum recommended. But under these conditions, they're recommending 40 to 60% RH. The reasons why: low humidity promotes rapid evaporation and promotes aerosolization of the cell nuclei. So when that happens, it hangs in the air longer, the smaller that droplet becomes. The science is still out on whether or not COVID is anhydrous resistant or not. So we're not quite sure if there's an increased viability in low RH settings, but a lot of pathogens are. So, there's that caution there as well. And also, many studies have shown that anything below 40% RH starts to impair the mucous membrane of the individuals. So it isn't so much about attacking the virus as it is about making sure that people's immune systems are working properly. And you start to see, a lot of sensitivity down in the 10 to 20% RH range. So we definitely never want to get down to that range. You know, again, the recommendation, we're going into winter, try and get close to 40, but we also want to be mindful of, you know, building envelope issues. So really understanding your facility and what you can do with your facility is very, very important at a time like this. And, you know, other studies have also shown, you know, again, there might not be a direct correlation with humidification on the virus itself. Again, it's more about how humidification impacts the individual and how they can respond to that virus. A couple more slides to go. So controls and energy here. So we've touched on controls kind of throughout. So this is another element here. We're going to talk about energy recovery systems specifically. The initial guidance was, you know, suspend use of energy recovery systems. That was kind of it from ASHRAE right at the beginning. That has since changed. You know, the idea here is that anything that's air decoupled, where you have a 0% risk of transfer, should continue to be used. If we're talking about bringing in outdoor air, you're going to need these systems because, you know, we have to be mindful of our energy use. They also suggest that low-risk systems, so systems that have less than 5% cross-contamination, are also acceptable. But what's important here is that you understand and you inspect your systems to make sure that they're running properly, that they're not in a state of disrepair, that you do not have excess leakage. Because again, a system will be designed for a specific leakage rate, but if there are gasket issues, if there are, you know, just wear and tear, you're going to start seeing more cross-contamination. So you really have to be mindful and do a thorough and proper inspection of your energy or heat recovery systems. And, you know, the guidance is also, if there happens to be an epidemic outbreak in your facility, to shut down that system and do a proper and thorough inspection before you restart it. So all the control work, all the automation that goes into your building is really where that rubber meets the road. So it's very important at a time like this. You're going to be relying on these systems heavily. You want to test and verify that all these systems work. If it hasn't been part of your maintenance plan, you want to recommission if you're not certain. I mean, if you haven't touched these things in years, maybe it is time to do something like that. You know, you want to review your damper operators, valve operators, sensors, whether it's humidity, temperature, schedules, your sequences. And again, you know, if you have pressure control, making sure that all that's working properly, because at a time like this, you're really going to need it. And I'm all out of slides. Rob, over to you.
Thank you very much, Raphael. And thank you, Marianne, both of you, for the great presentations today, particularly around HVAC system considerations when dealing with aerosols, which is obviously relevant to our response to the pandemic and our efforts to better protect employees, tenants, and the public. And thank you again to everyone that joined us today. And just a reminder, please complete the survey before leaving the presentation or afterwards. We greatly appreciate it. And I'll now open the floor to questions and also go to the questions that already have been entered on the Q&A here. So just a first comment here. A couple of you have asked about whether the presentation will be available afterwards. It will be, I think, posted on our website shortly, so you'll be able to get it there. So the first question is from Sean here. He's asking, can you comment on the differences between MERV 13 versus MERV 13A filters? I think Raphael's probably for you.
Yeah, I mean, if you'd want to look specifically at whatever filter you're going to pick, and just to see how it's going to perform across different particle ranges. That's really the best guidance I can give right now, because, you know, again, you can find, you know, different filters that will perform at different levels regardless of your of the MERV rating. So I don't want to just rely on the MERV rating alone. I want to look at the individual performance of each of the filters.
Okay, and actually, as a follow-up question, is the idea behind moving up to MERV 13 is the idea to trap the coronavirus? Is that the idea?
So it's the idea that, again, so as Marianne pointed out, the coronavirus itself is really, really small, right? So these filters might have a hard time just grabbing something that's at that range, but they're typically housed within a larger cell nuclei, which is larger than that. And, you know, as people are talking and aerosols going out into the space, you're going to catch these larger particles, and you're going to dilute, you're going to filter more contaminants out of your space.
Okay.
I don't know if that answers that question.
Yeah, I think so. Another question from Charles. He's asking, what is being recommended by others regarding CFM per person during the pandemic?
Well, I don't know if that's referring to the 20 CFM per person that I mentioned that we had identified as something that some of the experts have recommended. This was specifically in relation to COVID-19 prevention. And we have not really found a consensus or really much else other than that in the way of recommendations for ventilation levels. I don't know if you have, Raphael. But this was mentioned by one of the experts in presenting to an ASHRAE conference. It was also from Lydia Morawska, who is kind of a major researcher in aerosol science, who communicated that to me in a personal communication. So that's what we've been using. Raphael, did you have anything else on that?
Yeah, so if you look at, you know, if you look at even the ASHRAE numbers, I think where that 20 CFM might come from is you look at the typical office density that they have. It's on that table that I had provided previously. When you break down the occupant density, the area, you break it all down, it works out to about 17 CFM per person, but that's an uncorrected number, which doesn't really take into account the effectiveness of the delivery to the space or the efficiency of the system as a whole. So once you start adding those efficiencies, you'll probably find that, you know, that number is going to shoot up to 20 CFM quite easily. So, you know, those numbers aren't that divergent at all. So I believe that's where that recommendation is coming from.
All right, great, thanks. David is asking, where do you get MERV 13 filters for an existing residential ERV system?
Oh, that's a good question. I mean, there's a variety of suppliers that are out there. You know, I don't want to. I'm not here to push any specific product names or anything like that, but you know, you can find them online.
All right. Alexander is asking, what is your recommendation for airflow pattern in the space? For example, what are the? Oh, sorry, it's jumping around here. Sorry. What is the recommendation for airflow pattern in the space? For example, where are supply airflow in relation to the exhaust? So I guess that's to do with the layout of supply versus return, I think is what they're getting.
Yeah, so I mean, typically you'd want to move you'd want the clean air to sweep across the room, and then you want like your exhaust, or it's so dependent on what the room is, but generally you want to move from clean to dirty. Mm-hmm. So wherever your return or exhaust is, that's where you want your dirtiest air to be.
Okay. And actually, as I had a follow-up question saying, should the exhaust be at the source, i.e. at the entrance of the building? If that makes sense.
I'm sorry, could you repeat that? It glitched.
Should the exhaust be at the source, i.e. at the entrance of the building?
At the entrance of the building.
Exhaust. I guess the idea is as people come in, probably they're trying to capture it as people come in, but once they enter the building, you have to follow them throughout the building, I'm assuming, right? So not just the entrance.
Yeah, so you wouldn't typically put exhaust at the entrance of the building. No. And if we're talking about within spaces, you know, if you're looking at, you know, patient rooms, when we're talking about healthcare, you'd want, again, that exhaust point, you know, right near the patient. You know, the source contamination is where you'd want to try and control it. Okay.
Colton's asking, how was the target maximum CO2 level of 800 ppm determined?
So again, that is not a maximum number for all applications whatsoever. This is, you know, there's different requirements, there's different calculations that you follow when you're dealing with ASHRAE. There's very specific requirements around that, depending on your occupancy and the type of building. The guidance is more around when you do that calculation, which I believe is in ASHRAE guideline 36. When you do that calculation, take that number, and you know, if you reduce that by 20%, you're going to improve the response of your system. So it's more of a commentary on that, and it isn't a commentary on, you know, every single case is going to require 800 parts per million.
Okay.
If I can add, Rob, to that, when the ASHRAE standard of 1000 ppm for comfort was around, they found that 20% of the people who were exposed to air which contained 1000 ppm of CO2 complained. But when it was reduced to 800 ppm, that complaint level went down to less than 5%. And that's where the Ministry of Labor at that time decided that the target should be more like 800 and not 1000. And if you were to calculate 800 ppm of CO2 for a certain occupancy, that also translated to 20 CFM per person. So the 800 ppm and 20 CFM person, they are related to comfort. This was the pre-COVID times.
Yeah, and I think that's your point, I think the 800 is just a set, a reasonable lower number to, to get a little bit more ventilation than we had previously prior to COVID. And Amit, it's actually asked a similar question about, again, the 800 ppm and compare it to the 700 plus 300 outdoors, which is one of the previous ASHRAE standards. And I think you've already kind of answered the question. I think the 800 is a little bit arbitrary, but the idea is to be lower than, the previous pre-COVID standards.
Another way of explaining is that 700 ppm, in addition to the outdoor air, represents 2% of that air came from somebody else's lungs. And that was reduced to 1%, cut down by 50%. And that gives you almost half of that 700 that actually we're talking about.
Yeah,
so it means that only 1% of the air that you are breathing in came from somebody else's lungs.
Right, yeah, that's correct. Thank you.
Yeah.
David is asking, when changing the filters that are potentially covered with virus, what PPE should be required for the safety of the technician?
Sorry, could you repeat? I don't see that question.
So David is asking, when changing the filters that are potentially covered with virus, what PPE should be required for the safety of the technician?
Well, I guess that's
I think we can answer. Yeah, we can answer that
question.
Yeah,
it's kind of an industrial hygiene question. I don't know if you want to go ahead, Rob. Well, for one thing, remember the virus doesn't survive that long outside of living organisms. So I don't, it's not like it's a grossly contaminated and infectious filter. However, I think you're right to ask that the person changing it should be protected. So I would certainly recommend kind of standard protection against particulates, which should include a proper respirator, like perhaps a half face piece particulate respirator, an N95, plus eye covering, face shield or goggles, because we do know that the virus can be transmitted through the eyes. It's probably not a common route, but it can happen, as well as, coveralls and gloves, and certainly observe good hygiene after doing that.
Yeah, and I would just add to Marianne's point to make sure you also carefully handle the filter itself. Don't obviously drop it or let it kind of enter the airstream again as contamination. So make sure you put it directly into a waste bag, get it out of the air handling unit and into a waste bin as quickly as possible. Abdel's asking, has there been any input from ASHRAE to recommend more of a displacement ventilation design? Supplier at floor level and return at high level? And if this stratification reduced the probability of infection?
Can I mention that? Even then I'll turn over to you, Raphael.
Sure.
I would just want to refer people to a different document, not from ASHRAE, but from ACGIH, the American Conference of Governmental Industrial Hygienists, which has produced a document on industrial ventilation for COVID, which does have recommendations regarding displacement ventilation along the lines that you're suggesting. So I think you're on to something. I don't know if ASHRAE has produced anything like that, Raphael.
Yeah, I don't recall if they have specifically mentioned that or not. I mean, when you look at that displacement ventilation technique, it does improve the effectiveness and efficiency of delivering outdoor air to your space. So you can definitely make that argument that with the same amount of outdoor air, if you're routing it a different way, if you're doing displacement from ground up, that you're going to be able to control that pathogen much better.
Yeah, and I think you're also taking advantage of thermal buoyancy in that respect too, right? The natural airflow is going to go up anyway, so that you're emphasizing that even more and capturing that efficiency, like you're saying.
Yeah, so I'll be on. I think one of the reasons that I might not have seen any specific guidance on that now. I mean, first of all, it's difficult to make a design change like that. That's you do that for when the building's designed from the beginning.
That's right.
And I don't know if anyone's really looked at, if when we have droplets that settle on the ground, if they then get pushed back up into the airstream, so what that impact could be. So again, I haven't really seen it specifically, but I certainly haven't seen everything.
Okay. I guess this one's a similar kind of question from Hatham here. So let's with the next one here. What is from Ariane? What is the best practice to change the layout of the office space? It's a pretty general question, I guess.
So again, you guys have provided so much guidance on that already when you talk about spacing people out and doing all those things. I mean, but if we're talking about you know, HVAC and ventilation and how we distribute air, again, we want to look at how we're providing air to that space and go with that concept of pushing air from cleanest to most dirty, and then returning and exhausting it from there, depending on what type of system you have. But I hope that answers that question.
Yeah, and I'll just add something quickly there. I think in the past, in our previous presentation, we talked about, again, the whole clean and dirty concept, but also the number of people that are in the airstream should be minimized as well. So you shouldn't have air pass through 10 people, you know, it makes it pass through 1 or 2. So if you change the rotation of your furniture and your layout of where people are sitting, so that it goes from the supply to return with as few people as possible along the way, that would also be ideal. So that's, again, something to consider in terms of your furniture layout, is to kind of minimize how many people are in that airstream as it gets, you know, potentially contaminated over time as it passes through more and more people, right, before it gets to that return or the exhaust. So, okay. Carlos is asking, from design point of view, would you discourage the use of ductless units due to the lack of MERV 13 filter options?
Yeah, it's a good question. I mean, if we looked at that CFD that was done on that restaurant, that was a ductless split, so great catch there. If you're just pushing air around, I mean, anything that's just recirculating air that's not really filtering it is problematic. So I would agree that I wouldn't really be comfortable using something like that at a time like this if you can't filter it in any way. And one footnote would be, you know, if we have large destratification fans as well, the recommendation is definitely to stop using those because they're not providing you air changes. They're mixing air and moving it around a lot. And as you saw, that's just going to help move that virus around more than anything else at a time like this. Great question.
Yeah. Ina's asking, is there a standard or reference containing guidance for the use of UVGI in HVAC systems or in occupied buildings?
Yeah, I think that's IESA that governs that. There is, I can provide you some information. Ines, I know who you are, so I can get that to you.
Okay.
ASHRAE also has a guidance document on UV.
Yeah, they do. It's general, and because of the electrical aspect of it, there's more stricter regulations, and the one, I think it's ISNA that governs that.
Okay. Dimitri is asking, has there been any studies on particle displacement via air curtains at revolving doors or sliding doors?
That's a good question. I haven't come across any.
No, I haven't seen any studies or anything on that.
Okay, that's a good question though. Yeah. David is asking, as an architect designing long-term care homes, do you have any specific design considerations?
Yes. I mean, we want to make sure that we're designing these facilities properly. You know, that you want to try and reduce the amount of mixed air. You want to keep like the principles that we're talking about today are applicable to a lot of buildings. And, you know, in those types of facilities, you really want to be conscious of, if we have people that are ill, do we have the right areas where they can be, where you can move them and you can isolate them and you can treat them, so you can get them out of the, you know, general population. And really pushing towards more of a healthcare style approach to the design of those facilities is going to be very important.
Okay. Chuck is asking, you mentioned stratified supply and exhaust, and that you might stir up the virus on the floor. If the system was running all the time, would it have a chance to settle on the floor?
Good question. It might not. It might not. But again, the diffusers aren't everywhere, right? It's they're located in certain locations, so there are going to be locations where it could settle. then you walk around, you disrupt it, then that gets potentially kicked up and pushed around with the airstream. So again, I haven't seen much science or research on whether or not those systems are better or not with respect to this.
Okay. Is there any other sheet here? Let's see here. We also have CO2 we talked about, lower. Hannah is asking, can you move return air inlets to lower levels to make the system more efficient at capturing the virus, i.e. closer to the people? So instead of being up at the ceiling, maybe having them closer to the people themselves?
You know, it's going to be system specific, depending on how that system's designed in the first place. And, you know, when we talk about this thing becoming an aerosol, I can't really say if that'll be better or not. And, you know, when we think of a lot of open office settings, that would be hard to do. So it's going to be system specific, and again, facility specific. If we're talking about, you know, treating patients, that's one thing. You definitely want them right at the source, because when we know that they're really sick, they're expelling a lot more load. You know, in a typical office setting or you know, maybe even a school, that might not be possible to do. And it might not work properly with the system as a whole. So it's hard to answer that in isolation.
Yeah, you have to see the layout. Amit is asking, as I'm making a comment as well, in Indian ASHRAE standards, is recommended one more method to clean return air pass through aeration tank, which holding 1% sodium hypochlorite solution with diluted COVID virus. Can you share your thoughts on this?
Can you please repeat that?
So in Indian ASHRAE standards, it is recommended they recommend one more method to clean the return air. They pass through an aeration tank, so I guess with the solution in it, which holding 1% sodium hypochlorite, so basically bleach, which dilutes, I guess, the COVID virus. I think they mean probably, you know, kills the virus. Can you share your thoughts on this?
I'd have to see more research on that before I can give an opinion on that. Sorry.
Yeah. Another question is, by using a particle counter, can we identify the efficiency of a ventilation system?
Yes.
No. Okay. Another question here from Irina. Do you recommend doing flushing 2 hours before the building is occupied?
So that is an ASHRAE guidance right now to do that. We certainly don't recommend that you run it 24/7. So, you know, flushing before, after seems to be the approach right now. You know, some had suggested 24/7, but that's excessive, because that, you know, the virus isn't going anywhere when no one's in that building, and that 2-hour flush will be generally more than sufficient to change out the air and dilute.
Yeah, agreed. Let me just check the list here. I think we might have gotten to everybody. Yeah, I think looks like that's all the questions, so that's great. Oh, and it's another comment here, sorry, from Chuck. Just a comment. For retirement homes, we have considered zones to isolate people from the general population, but from an operational and occupant perspective, we determined that it might be disruptive and uncomfortable for the resident. So I'm not sure what their comments are trying to say there, but
I think that was just in response to the suggestion around, you know, isolating people when they're ill, right? So that comment is in response to, there's some, you know, I'm looking at it from two different perspectives, you know, whether it's a new or existing facility. There's a lot of existing facilities where you just might have to do that, because some existing long-term care facilities haven't been designed where you have proper ventilation in rooms, and you don't have, you know, potential cross-contamination or anything like that. So, you know, when someone is ill in one of those types of facilities, I know might not be the best for the patient, but we got to think of the people as a whole, and you want to consider doing something like that. But in newer facilities, again, if you're designing your systems properly as well, right from the beginning, where you're avoiding cross-contamination, you're providing the right filtration, the right amount of airflow, and again, good directional airflow would definitely be important. You know, designing it right from the beginning is always the right approach.
Yeah. Great. Another question here from Nicolette. In schools with classrooms that only have windows for ventilation, what would be the best approach to improve ventilation, especially if windows can't be easily opened during the winter?
Yeah, so that's definitely a challenge. I know that you guys had provided some guidance there on, I mean, we can talk about ventilation. I mean, unless you're putting in a system, you're not going to get any more ventilation, unfortunately, right? So, you know, you can talk about other strategies to try and contain or filter, dilute, whatever. I mean, there's approaches. So the one you had talked about your last webinar, bringing in HEPA filtration units, is definitely a good approach. The UVGI that we talked about is another potential approach, because again, that's the equivalent of 10 ACH. But you know, you still have to have fresh air. So, you know, inspecting those units, making sure that they're running properly, making sure that, again, they have filters if there's any type of recirc on them. You know, because I think she mentioned it's a window unit, or there's just windows as the fresh air source. I wasn't clear on that.
Yeah, I think that person was basically saying that if you only have windows, but I know from what I've seen from even the older schools, they almost always have exhaust ventilation in the classrooms, even if they don't have supply. So if you make sure that's running properly, that's another way to benefit to get the air changes that you need, right? Through using those exhaust systems and use them as much as you can. So I think we're already pushing at 12:45 now. So I think we'll stop the questions there. But however, if anybody has any questions, please do email us and email Raf as well, and we can definitely reply to your questions. But just in courtesy of everyone else that's already been in the call, thank you very much for joining us and sticking around with us for the questions. There's a lot of great questions there and discussions. So thank you to everyone. And thank you also to our presenters, Raphael and Marianne today. Great job, guys. And have a good afternoon, everyone.